Hi, people. It's time to start talking about some more complex systems, some more complex phenomena, perhaps. And we talk here about the accelerating system. And one of the reasons we're doing this right now is you've just looked at, a lot of you, at a system that accelerates. You've looked at a mass hanging over a pulley that makes a cart accelerate. All right. Well, when we say that the mass makes the cart accelerate, it's not really the mass. It's the fact that gravitational force acts on this mass, and that gravitational force makes the cart accelerate. Well, the gravitational force of this mass makes what we call the whole system accelerate, not just the cart, because there's this cart and then there's this mass. So we have to start talking about systems of objects, all right, and how we can analyze, well, parts or the whole thing, all right? Here's an example with three masses being accelerated by that 42 Newton force that acts to the right. They're objects of differing masses, a rope between this 3 kilogram mass and a 1 kilogram mass. So what we're going to start with is looking at free body diagrams for 4 different things. First, mass 1. The 1 kilogram mass. Let's look at that. All right. For the 1 kilogram mass, here's a free body diagram. Let's see. Well, it certainly weighs something. There's a normal force exerted on it. There's a tension force like that comes from this rope. Now, if I'm careful and we look at this, there you go. What we really sort of want to be able to do is, and it's tough that this is 3-dimensional, so I might actually simplify it and make it 2-dimensional. And if we have the 1 kilogram, the 2 kilogram, the rope, the 3 kilogram, what we're actually sort of doing is this. We're saying, let's isolate stuff in that box. Now, I understand the 2 kilogram mass looks like it's sort of in the box there, but it's not. We're trying to isolate the 1 kilogram mass and forces that act on it. I guess that's what we started doing on the left in our free body diagram. But there's another force that we haven't drawn. All right, and maybe we'll circle back to that in a minute. But one of the things we do want to show, I should point this out specifically, is look, if this is a rope and we're isolating part of the system and our little isolation box here cuts across that rope, well, we have to identify that as a tension. All right, so that's where this tension comes from, the fact that this rope is pulling out of that box. Okay? All right, well, let's take our little let's take our mass 2 and look at that. We'll circle back to mass 1 in a second. So here's this one. It's got an mg like that. It has a normal force that looks like this. I'm trying to draw it twice as big as the mg for this one because it's twice as much mass. And well, the only reason that M2, what I call the 2 kilogram mass, I call it, for notation's sake, I'll call it M2. I'll call this one M1. All right, the only reason that M2 accelerates is because there's a force that, well, object 1 exerts on it, and that's a normal force. It comes from the surface contact between object 1 and object 2. So I'm going to say that this is a normal force that 1 exerts on 2, as opposed to the normal force here that the Earth exerts on 2. So we talked a couple days ago about using some notation specifically with normal forces and well, with any kind of force, really, it's a good idea sometimes to be able to talk about what's the force exerted by and what's the force exerted on. All right, all forces are two object or two system interactions. So being able to identify those two objects or systems can be very, very helpful. Now, a lot of you will notice we have this normal force that one exerts on two. That means that by definition, there has to be a normal force that 2 exerts on 1. And furthermore, it has to be in the opposite direction. These are what we call a force pair. Right? Those two normal forces. Force pairs are the same type of force that two objects exert on each other. Newton's third law says those two forces have to be exactly the same size and point in opposite directions. I didn't do a great job of making them exactly the same size. Shame on me. Okay? So now we have identified all the forces acting on mass 1 and mass 2, M1 and M2, the 1 kilogram mass and the 2 kilogram mass. All right? If we were to draw our little isolation box here around object 2, you notice there are no ropes pulling on mass 2. It's in contact with this surface. It's in contact with that surface. So therefore, there are two normal forces acting on it. Okay? Okay, now for the mass we'll call M3, right, we can do this. And here's what we have. If we say this is the 3 kilogram mass that I'll call M3, well, I guess I can't really make a 3 times bigger mg, but I'll just make that. And I'm going to, how about this? M3g, good notation there, M2g, M1g. All right, here's a normal force that the Earth exerts on 3. Well, we have this 42 Newton force because they tell us we do. And then we have this tension force that pulls this way. Right? Our little isolation box here cut across a rope. We turn that into a tension force. And look, we've got another force pair. Right? This is really, over here, if we look at M1, this is a tension force that 3 exerts on 1. So therefore, this is a tension force that 1 exerts on 3. A nice equal and opposite force pair. Okay? Okay, I'm going to try to, let's see, make these a little smaller. Groupity group, group, group. You move it, you get smaller. Find this. I'll group that up. Make this small. Group this. Forget about that. Delete. Just make sure you can identify those force pairs. My blues and my reds are force pairs. Notice, opposite direction, same kind of force. Now, the other thing we want to look at is the system. Now, the system for us is everything that accelerates. And this is the system, everything in the box. So, we do this. The system weighs something. How much? Well, it weighs M6. Get it? 6 kilograms worth. M6G. Fair enough? There's a normal force that the Earth exerts on the system. Well, there's this 42 newtons that something, well, I don't know what kind of force this is, if it's a rope or I don't know what it is, but it's there. And we're done. Now, one thing that we haven't made explicit, well, they tell you, but it's frictionless. There's no friction between the Earth and the system, or the ground in the system, you know, whatever you want to call it. And then what about like this tension force and the or like these normal forces exerted here and here? Well, notice that that tension force, you know, like here's my red force pair of tensions, and here's my blue force pair of normal forces. Well, those are in the box. Those are in the system. Those are parts of the system exerting forces on each other. All right? And so what we're doing when we look at the system is looking at interactions between the system and the outside world. This 42 newtons comes from something else. We don't know what it is, but it's not the 3 kilogram mass somehow exerting that 42 newtons of force. That doesn't happen. All right? This, right, is a force that the Earth exerts on the system. This is a force that the Earth exerts on the system. So those are not parts of the system exerting forces on each other. Okay, so you notice that what else is true about these, what we call interior forces, these force pair forces? Well, they add up to 0. All right, so as far as Earth's interaction with the system, those are the only forces. And the question is, you know, why 4 free body diagrams? Well, you might not need 4, but in any good accelerating system, or you know, multiple, we call sometimes multiple mass system, in any good problem, you're going to have to use at least a couple of these in an analysis. The question is, you know, which one do you use? Well, in a lot of cases, the system equation is the one, or the system free body diagram is the one that can get you started the easiest. And in this case, in this question, that is the case. It says determine the acceleration of this system. Well, I mean, in acceleration, we're going to have to, you know, look at a net force equals ma statement, right? A Newton's second law statement. And the question is, where are the least number of unknowns? If you look over here, we don't know what the tension or that normal force are. Here, we don't know what that normal force is in the left to right direction. Here, we don't know what that tension is. But here, if you notice, there's really only one unknown. If we started here and looked at direction x, the horizontal direction, well, this just says that, well, 42 newtons equals m system A. And we know the mass of the system. It's 6 kilograms over mass of the system. So the system accelerates at 7 meters per second per second. The system accelerates at 7 meters per second per second. Well, what does that mean? It means all parts and the system have the same acceleration. All right, if the 3 kilogram object changes velocity at a certain rate, it's physically connected to the other one, so do they. So we've just found the acceleration of every object because we were able to find the acceleration of the system. All right, so when we look at part B, find the tension in the cord connecting the 3 and the 1, well, that means we're either going to have to use this one or this one. The question is, where are there fewer unknowns? And then when we get to part C, so for part B, tension in the cord. Look, here's the tension. Here's the tension. You got to use one of those two. When we get to find the force exerted by the 1 on the 2, well, that's this. or this. So it's going to be one of those that you use. So what I want you to do, for next time I see you, is finish this problem. You have all the free body diagrams you need. Okay? Okay. Now, here's another kind of one of the most standard kinds of what we call multiple mass systems or accelerating systems. It's called an Atwood machine. Charlie Atwood was a big, he hooked a lot of masses over pulleys and just went crazy with them. I'm sort of kidding there. So when you let this system, when you release this system from rest, it will start to accelerate if there's a difference in these masses. Here, maybe you can follow along logically that M2 would have to be more massive than M1. All right, so if we look at each block separately, I'll do a free body diagram for M1. All right, so for M1, we have M1G and we have tension. Yes? Now for M2, let's see, we have, I'll do it over here. We have M2G and tension. Now, the weird thing about this is that this rope changes direction, but it's all the same rope, this rope here. So if it's all the same rope, again, that can create a force pair for us. And even though those two T's in my free body diagrams are pointing up, those are actually the opposite direction. Pulling up on 2 and pulling up on 1 is the opposite direction. Because what we have to sort of say is, if this system accelerates that way, then anything in that direction, let's call positive. So for M1, up is positive, because M1 accelerates this way. For M2, down is positive, because M2 accelerates that way. All right, that's a tricky thing with a lot of these problems. But sort of get an idea for what direction the whole system accelerates, call that direction positive. Positive equals direction of system acceleration. So we can write two net force statements, right? Net force equals ma for 1. Well, that would be like this. T minus m1g equals m1a. Again, for m1, upward is positive. Okay? For mass 2, net F equals ma. This one's going to go m2g minus t equals m2a. Now but just notice, if I'm looking at each part of the system individually, that's why I do this. On the last page, I did a net force statement equals m system A, but that's when we were looking at the whole system. Now I'm looking at each mass individually, so I use the mass of the part I'm looking at. Okay? Now, what we can do with these two statements is we don't know what that tension is, and we don't know what the acceleration is. Let's assume we're given M1 and M2. All right? But we don't know what the tension is. We don't know what the acceleration is. But remember, this is an accelerating system. Both parts of the system have the same acceleration. And this is the same rope. These tensions are the same. That's a force pair, equal and opposite. Okay? So what we can do is set these two equations well, how about this? Here's what I'm going to do. I'm going to set the T's equal to each other. So over here, T is going to be M1A plus M1G. just move that over here. Over here, I'm going to move the t over here and move that over here, and I get t equals m2g minus m2a. And now I can set those two expressions equal because same rope, same tension. So I get the following. Let's see. M1A plus M1G equals M2G minus M2A. The only unknown here, assuming we know M1 and M2, is the acceleration of the system. Well, let's find it. I'm going to put all the A's on the same side, and I'm going to move everything that doesn't have an A over there. M1A plus M2A equals M2G minus M1G. Factor out A. M1 plus M2. M2G minus M1G. Solve for A. Divide both sides by the sum of the masses. All right, there's an expression for the acceleration of the system. Right? The top part is really the net force. Right? M2G is the weight of the second object. M1G is the weight of the first. And the difference in their weights is the net force acting on the system. Right? And remember, the net force makes the system accelerate. There's the mass of the system. Okay, so we can go through this two unknown thing to find an expression for the acceleration of the system. We could then take that and plug it back into either one of these expressions, the green or the red here, and figure out what the tension on the string is. All right? That's a pain of a way to do it. Okay? There are times when you have to look at each part of the system individually. But there's also times, as we've seen here, where looking at the system itself as a whole can make your life easier. And it can be the same thing if we look at the system as a whole here. So, if you look at the system as a whole, I want you to see what happens. Yeah, next page. Yeah. We can sort of say that the system is, well, the two masses together. And it's kind of like when we release this thing, it's sort of like this whole system accelerates in whatever direction we call positive. Remember we said, this way is the positive direction. Up for 1, down for 2. So up for 1, down for 2, that's sort of like, it's sort of like saying it all accelerates this way. See what we're how we're sort of trying to simplify this? So if we look at the system, we can sort of say, well, we're doing this. We're saying let's isolate everything inside that box. Right? Now there are tension forces inside that box. Right? M1 has a tension force that acts upward like this. M2 has a tension force that acts upward like that. Those are parts of the system exerting forces on each other. If we're looking at the system, we don't talk about those forces. We want to look at forces where the outside world exerts a force on the system. And those gravitational forces are forces from the outside world. They're the Earth exerting forces on M1 and M2. And what we can do is say that, well, if, like we said before, this is our positive direction, well, we can sort of say that, well, this is our positive direction. Well, M2 experiences a force in that positive direction, and it's M2G. M1 experiences a force in the opposite direction, M1G. So if we look at a net force statement for the system, we can say, well, the forces are M2G and M1G. I subtract because this one's to the right, that one's to the left, and this equals MA. Well, what mass? If we're looking at the system, it's the whole darn thing. And boom, right away, we're at one expression for acceleration. Before, we had to go through two equations, isolate parts that were equal, set those expressions equal, and then do some factoring and all that stuff. This is, boom, M2G minus M1G. Mass of the system, remember, is just the sum of the masses. And we have the same exact expression that we had here, but in a quarter of the work. Way easier. Okay? Let me shrinky dink this. Oh my. This stuff. Yeah, I'm going to take this stuff. Good. Now, let's assume that we wanted to find the tension on the rope. Yeah. Well, remember, tension only acts on part of the system. So that means if we want to find the tension, we've got to look at one part of the system or the other. Let's just choose to look at mass 1. Here's M1G. Here's tension. Our net, that shouldn't be an X. Forget about the X. Our net force statement, remember, upward is positive for mass 1. T minus M1G equals MA. Well, what mass? We're looking at mass 1. We've isolated mass 1. So that's the mass of the object that we look at. All right, so the tension is M1A plus M1G. Well, then all you have to do is take all this, whatever number you get, just use that there. The rest is pretty easy. I mean, it makes an algebraic, a big ugly algebraic expression if you do it all algebraically right now, but we have to assume that this might be part A of a question, find the acceleration of the system, and then second, find the tension on the rope. Okay? That work for you? Okay. We are going to, I'll hold this till we get together next time. All right, these are actually a little bit simpler. It depends if they're simpler or not, depending on your, depends on your outlook. So yeah, next time we look at, we'll do this one together, and then we're going to look at an Atwood's system and use it to do something of value. Okay? Next, we'll do a little experiment with an Atwood's machine. Okay, people? Okay. Adios.